who's going to talk about Gaussian processes for global optimization.
So, well, thank you all for coming this morning, especially those of you who went to the brewery yesterday. I hope you have fun with that. Microphone. Yeah, sorry.
Is it working? Great. So this talk is going to be about Bayesian optimization. This is a change that we have introduced in the Gaussian process this year with respect to what we have in previous editions, in which the third day was more about Gaussian process latent variable models, but you already saw some of that stuff on the second introductory talk that Neil gave and then Alan gave as well. So so far what you have seen in the summer school is that, well, Gaussian processes are very powerful tools to do modeling, right? To do probabilistic modeling, and you can do all sorts of stuff with this type of techniques, right? So you can do regression, you can do classification, and many other type of things. So this talk is about how you can use Gaussian process to solve a different type of problems, which are not necessarily modeling problem, but in which somehow there is a model involved to solve the problem that you have. So you can think about having a problem in which you want to calculate an integral, or solving a differential equation, or an optimization problem. All these problems appear in the numerical analysis framework, right? There is a new area of research now that is called probabilistic numerics, and tomorrow you will have Philip Henning and Mike Osborne here talking about this, and they are covering a range of applications of how to use these probabilistic methods to solve these types of numerical analysis problems. But here we are going to focus on this particular case, which is how to solve global optimization problems. So so the first part of the talk will be a general introduction of these techniques, because tomorrow we will have the whole day for this. And the last part of the talk, I will use it to explain you some things that we are doing here in Sheffield about Bayesian optimization and this type of technique. So essentially, this is the problem what we have. So we have a function f that we suppose that is a well-behaved function. That's kind of a fuzzy definition of what we have, but we assume that the function that we have is something that is continuous, that is well-behaved, etc., etc. So that is defined in principle in a compact set. In most of the examples that you will see, the function will be defined in some box like this, but you can think on more complex domain. We will touch this. So the idea, the problem that you want to solve is to find the minimum of this f in this domain in which the function is defined. Okay, we all know this problem. When we are kids, we start solving these problems. When you have a function, we take the derivative of it, we calculate the critical points, we have the minimum of it. That's fine. Okay, but obviously what we are going to talk about here is about more complicated version of this problem that we all know since we are kids. First, because f is going to be a function that is explicitly unknown. So we will see. Yeah.
Oh yeah, one question. Why are we only looking at compact sets?
Yeah, that's a general definition. We can have a look to other type of domains. So f is explicitly unknown. So we don't have it explicitly, but we have access to it through some evaluations, right? These evaluations can be even expensive. They can even be perturbed by some noise. Right? So you can think about the type of functions that we are talking about functions that correspond to the evaluation of some computer model, and the evaluations are expensive because it takes a lot of time to get the output of the function, or because the function is embodied in some physical process and you need to run a lab experiment to get an output of it. So these evaluations are expensive, and the function is multimodal, and the evaluations can be perturbed. So if you think about this problem, and if you think even in the case in which you could have access to exact evaluations of the function, you say, well, if I want to solve this problem exactly, if I really want to with an arbitrary precision to find a location in the domain which is close enough to the optimum that I'm looking for, you could do some grid search. Why no? You could start evaluating in a grid of the domain. But the problem is that the number of evaluations that you would need, if you assume that the function that you have is Lipschitz continuous, so basically you assume that, sorry about that. So if you assume that you can bound the change of the function that you have by some Lipschitz constant, so x1 and x2, they are in the domain in which the function is defined. So essentially, if you assume that you can bound the change of the function by some positive constant L, you need this number of evaluations. So in a functioning with the Lipschitz constant instance, so basically you allow to change the value of the function 10 units times the distance that you have for the two evaluations, the number explodes, right? So you can do that. You can do random search, random evaluations of the domain, but this is not going to guarantee anything in principle with respect to how good you are solving the problem, right? So if you think about this expensive function that we are going to talk about today, I want to ask you, and I want to find yourself in the position where you had a problem like this before. So this is a clear application of what Bayesian optimization does. So you can use the techniques we are going to talk about today to solve, to tune parameters of machine learning algorithms. So you can imagine a deep model in which you have a number of layers, a number of weight penalties, etc., and you want to train the model for a very large data set. Every evaluation of the model for a set of parameters will take probably hours. So to tune the parameters is going to be difficult. You can think any other machine learning model that depends on some parameters, and in the lab today you will use Bayesian optimization to tune the parameters of a support vector regression, for instance. But you can think about any model that you have in mind. Another example is A/B testing. A/B testing. So imagine that you are designing a web, and essentially what you want to do is to maximize the number of customers going to the web, maximize the number of signs up in your site, the number of downloads, etc., etc. So you think about this web. So you think about this yellow square where you write the location where you want to travel. You can parameterize these like different locations in the web, like different size, etc., etc. So every time that you want to know how good you are doing with the design, you can you need to keep the design of the site for some period of time to count that. So that's going to be timely cost. Or you can think about experiments or examples in computational biology, and this is something we are doing here in Sheffield, and I will talk about this later, in which you have cells that you want to use as mini factories to produce proteins of interest. And in this case, what you want to do is to optimize the genetic code of the cell so you can engineer the cells to produce more of the protein in which you are interested, right? So these are three examples, but of course there are many others. But the common idea is that everything is very expensive to evaluate, and that's why we need to use an heuristic that will solve the problem for us instead of doing the grid search that we were commenting before. So this is probably the most important slide of the talk. Yeah.
Yeah, in the beginning you said that the function might be perturbed.
Yeah.
Does it mean that for certain parameter values the function might give slightly different
Yeah.
outputs?
Yeah, exactly. If you think about these experiments, for instance, if you change the genetic code of the cell, you are going to have a measure of of the amount of the protein that you are producing. But that measure, because it's the result of a lab experiment, maybe not exact. Maybe it's not exactly what the cell is producing, but it's just perturbed by some noise. So with the techniques, with Bayesian optimization, you can basically cover both cases, and we will see how to do that. So what I was saying, this is probably the most important slide of the talk. So basically, this is the situation in which we are, right? So there is some function. I know the function, but you don't know it. So we have 4 evaluations of the function. I'm telling you that these are exact evaluations of the function, so we are not in that case. We want to find the minimum of it, right? So there are 2 questions that we want to solve here. Where is the minimum of the function, and where we should take the next evaluation in case of having budget for that. So if I ask you, what we know about the function is that it takes values here, and we have an idea of how much the function is changing in those terms. So we know that for this distance, the function can change this much. So we can already have, and if we assume that it's a continuous function, we can already have an idea of how would be the shape of the function that we want to minimize, right? So if I now ask you, okay, where do you think the minimum of this function is? How many people in the room think that the minimum of the function is exactly in this location? How many of you? 1, 2, 3, 4? Okay. How many of you think that the minimum of the function is in this region here? More? A volunteer. Why do you think that the minimum of the function is over here? Any special reason for that?
So one would expect that it's maybe somewhere close to the lowest cross.
Uh-huh.
And it should, I would expect it's more likely to be on the left of the cross than on the right, because the neighbor on the left is lower than the neighbor on the right.
Okay, that's a very good reason. So actually, what you have in mind is now a model of how the function looks like, right? It's a function that is going through these points, and that can be actually something like this, right? So yeah, that could be a function that it goes through the points that I have. Well, there is some sort of symmetry here that is going up here, is also going up here. So yeah, if we have a look to the minimum of the function, it's exactly somewhere here, right? So, but you have that model of the function in your mind. But if I ask some other people, probably each one of you have a different model of the function in your mind, right? So you can have something like this. So maybe some people think that it's like this because, yeah, this is going up, but maybe with the same level of change, the function is going down here, right? That's fine. Or maybe some people think that, no, I think the minimum of the function should be, as some of you were saying, is very close to the best found value that I already got, right? So I can repeat this process over and over, and I can ask everyone in the first row, and we can start building our beliefs about the minimum of the function that we have, and we can ask more and more people, right? So at the end, what is happening here? So I'm asking every one of you, what do you think about the minimum? And what we are doing is basically building an histogram about the belief that you have about the function, right? So somehow you are generating by this conceptual model that you have in your mind about the function, your belief as a group that you have about where the minimum of the function is. And we can imagine, well, let's do this infinite number of times, right? Let's repeat this many, many times. So we will have something covering the range of the data points that we have. And if we think about the histogram that we have created, let's think about the infinitesimal case of that. What we have created is a probability distribution that represents our beliefs about the function that we have. So if you think about what just happened here is, well, given just some points about the function, we made some prior assumption about how we think the function looks like, and we have built a function, a surrogate function that represents our current beliefs about where a property of the function, of a property of the function, in this case about the minimum of it. You could obviously think about, not thinking about the minimum, you can think about, well, imagine that I'm interested on the gradient of the function, right? So you could, the location of the maximum gradient of the function, you could exactly do the same thing. You could exactly play the same game and reconstruct the distribution about the gradient. Or you could do the same for the integral of the function, right? And you will be solving a quadrature problem, right? So this is exactly what happened, and this is the key of Bayesian optimization. So we have some prior model of the function that we have some data, and we construct an object that can be a probability distribution or another type of object that we will call acquisition function that will help us to query the function that we are optimizing over and over until we get close to the optimum of it. Of course, you can think about this. We did this with the minimum, and we reconstruct a probability distribution. But you can think about, well, I'm not going to check which is the minimum in each location. I'm going to check what is the expected marginal improvement that I have. So I can come here and say, well, if I have this function over here, I'm going to calculate which is the expected gain that I will get if I query the function in this location. So this is essentially the idea why, in which Bayesian optimization is based, and this is why it works. So it's a methodology to perform optimization of multimodal functions. You see, these ideas have been around for decades, right? And it's now when these things are exploiting and when we are starting to use Bayesian optimization to solve real problems, and we will discuss why that's the case. So the idea is, well, now formalizing things a little bit more. So we will choose a prior measure. We will combine that with the observations that we have. We will build another object that is going to be an acquisition function, and we will query the acquisition function to get more data to repeat the experiment over and over until basically the budget that we have is over. This budget can be of different types. It can be a budget in terms of the number of evaluations of the function, right? It can be a budget that is defined in terms of the time that you have to evaluate the function, of a cost, which you can imagine about having different cost of evaluations in the different locations of the domain, and you have to select that, etc., etc. But essentially, that's the idea. So what I'm going to do now is basically to visit these two elements, which are the key of Bayesian optimization. The prior measure, I guess I don't have to say so much about that. You all have in mind what you have to do here. But I will stop by here, gaining some more intuition about what this acquisition function is doing. Right? Any questions so far? Clear, right? OK, so prior measure, you all know what you have to do. So you have been doing Gaussian processes. Gaussian processes are nice models to deal with uncertainty. The posterior mean and the posterior variance have close expression, but you can also have other models to do this. But I prefer to use Gaussian process, and I think Nando de Freitas is going to mention in the next talk other type of models that you can use to solve this problem as well. So basically, I don't have much to say about this. You know the properties. In case of having functions, or having in mind that you have functions with other properties, you could go, of course, for other type of models like Alan, the type of models that Alan was mentioned yesterday. But this is the idea. So you define a probability over the functions that you have, and now we need to build this object. So we already built one of them. That was the probability distribution about the function. The nice thing about Bayesian optimization is that when you build this object that acts as surrogate of the original problem that you have, you always, and we are going to check this with some examples. So all acquisition functions that you can imagine will balance between two important terms. Something is called exploitation, right? So if you think about having a Gaussian process and collecting the new location where the value of the mean is very small, you are essentially exploiting what you know about the function that you have, right? Or if you think about collecting new data points in regions in the space where the degree, the uncertainty is very large, you don't know what is happening with the function there, but potentially there could be something interesting to have a look. So that's called exploration. So any acquisition function that you define, and we see some of them, are essentially balancing between these two terms, between exploration and exploitation, right? And an example of how to do that. So I thought, well, let's do this with beers after the beers tasting. But I like you to think when you go to a restaurant and you select the food that you want to eat, you are essentially maximizing the utility, your function of utility of the function that you are eating, right? So you essentially can. So this is a discrete design space, but you can, if it's a restaurant that you know, and you have a prior in your mind about the things that you like and the things that you don't like, you can go to the restaurant and say, well, I'm going to exploit what I know I think is going to be good, either because I know I like it or because I know they prepare it well in this restaurant, or I'm going just to explore, and I'm going to select things that I have never tried but could be potentially interesting for me, right? So there is this paper, I think it's an interesting one, which is the Bayesian optimization explained human active search, right? Because it's actually the way you make decisions, right? So you have a prior of the world, and you try to maximize your utility, and you are constantly balancing between exploring new decision or exploiting what you already have. And different people tend to explore more or to exploit more what they have, right? Okay, here in this example, this happens because you can assume that there is correlation. So if the quesadillas are good in this place, I can maybe try another one, right? Because they're going to correspond to points in the space that are going to be related, right? So that's the idea. So I'm going to show you different acquisition functions that are commonly used in Bayesian optimization. So the first one is called upper confidence band. This is a very intuitive one to explain this balance between exploration and exploitation, because, well, you have a Gaussian process, so you have the mean, and you have the variance or the standard deviation of the Gaussian process. So if you simply take the mean and the variance times some constant, this constant is representing that balance between exploration and exploitation, right? So you could think, yeah, if I drop this constant, so this is minimum. So what I'm representing, and I will do, just to be coherent, the same for all acquisition functions I will show, is the problem that we have is a minimization problem. The best point that the acquisition function is giving me is the maximum of it, right? So in this case, because I'm maximizing, that's why I have this minus term here, right? If I were, because I'm minimizing, I have this minus. If I were maximizing, I would have I would not have this here. So essentially, you say, well, I balance these two terms. This k, the larger this k is, this value is, the more I'm going to explore. The smaller this value is, the more I'm going to exploit, right? So this is another acquisition function, and I think tomorrow David is going to talk a lot about expected improvement and null extensions that you can have of it. So what you are trying to do here is essentially to calculate in each point of the domain in which the function is defined the marginal gain. The expected marginal gain that you would get if you were evaluating the function at that location. So essentially, this is the integral over the y, which corresponds to x, which is a point in the domain. So if you expect to get something that is worse to the current best that you have, basically the value of the acquisition function is going to be 0. So we know that these are exact evaluations, right? So basically here, the value drops to 0 because we know that this is already small. And we now look what the acquisition function is saying. Well, if you can take a new evaluation, probably the best is to take it either here or here. And it's balancing already between these two terms, the exploration and the exploitation. And it's doing that because, well, the value of the function is lower here, but you still have some large uncertainty. So probably it's worth exploring this point over here. So that's the expected improvement. You have another thing, which is called the maximum probability of improvement, in which you essentially are trying to calculate which is the probability that if you evaluate the function in some point x of the domain, you will find the minimum there. You can go to the reference to see the details, but that's essentially what you are calculating and the way you can obtain that value. There is actually a discontinuity here because you see that this is divided by the standard deviation. So basically, this is just if you have a standard deviation which is 0, so basically you assign 0 to that location because you are completely certain about the value of the function there. So that's another one. So this is information theoretic approaches. These are very interesting, and these are kind of the extension of what of the example that we were creating at the beginning of the talk, right? So essentially, you remember we created this probability distribution, yeah. So to do that it can be complicated, and it requires some approximations. It's not straightforward, but you could say, well, I'm going to use directly the probability distribution to select the point, so I can go to the mode here because that's my belief. Actually, you don't do that. You do, yeah.
Sorry, I was just going to ask. So this probability distribution, you don't actually have it though, because the GP is like non-analytic.
Yeah.
Sample the GP.
Yeah, you don't have it. And so these two papers, Philip Henning proposed to do Bayesian optimization using this probability distribution and by maximizing the decrease in entropy. I will mention that now. But you don't have this, and essentially these two papers, they propose different approximations to this probability distribution. So it's true that you don't have it, but I don't want to go into the details of how you compute that, because tomorrow we will have Philip and Matt Hoffman here, and they will give all the details about how you do this in practice. Yeah, it's not analytic, so you need to approximate that, and they propose two different approximations. Yeah. So this is not the loss function that you use when you collect a new sample. Essentially, what these two papers do is, well, I have this distribution here. I can calculate the relative entropy of this distribution with respect to something that is flat. So the information that is giving me, the location that is giving me the largest amount of information about the minimum of my function is that location, such that if I sample there, I will reduce the entropy of my distribution the most, right? So essentially, you have the entropy of the probability distribution of the minimum, and you have minus the expected entropy that you would have if you were sampling the function in the location x, right? So, but I won't go into the details, but you will have more of this on tomorrow. But this is essentially the idea. More. Okay, so you can do something that is Thompson sampling. And it's somehow what we did in the example, but just for one of you, right? So something you can do is to say, well, this is my GP. I'm going to draw a sample of it. And I can calculate the minimum of the sample, and I use that as a new point to evaluate, right? So Thompson sampling, I think the first paper in Thompson sampling appeared in 1933 in Biometrica, and it was developed for discrete spaces. And there is a whole literature about Thompson sampling and different things that you can do with it. To extend Thompson sampling to continuous spaces is not straightforward, and that's actually something that you need to do if you want to do some of the approximations. So you can imagine if you want to approximate this probability distribution, you can do by doing Thompson sampling. That's something that we did in our sample, right? But you need some technicalities and some theory to do that, which I guess Matt Hoffman will be describing tomorrow. Because so what you have done in the lab is essentially to generate a discrete grid, right? When you generate samples from the GP, but actually you want to use this for a real example. What you need to create is actually an actual function that you optimize. So you don't want to do in a grid. So essentially, you need to approximate samples from the GP in continuous samples from the GP. But I won't go into the details. So these are all acquisition functions, right? Not all, I say some of them. What they do is actually, so we started with this problem, right? So we started with a problem in which we have a function f that was very expensive to evaluate. From which we wanted to calculate the minimum. That's a problem that we couldn't solve. By means of the acquisition function, or by means of this reasoning that we did, we have essentially transformed this problem in a set of problems in which this function, this acquisition function, is essentially inexpensive to evaluate. The gradients of this function are available, so you can think about using gradient optimizers to find the maximum of them. But obviously, you still need to solve this set of problems that you have, right? So you can do that by different methods. You can use gradient methods, covariance matrix adaptation methods, or the direct algorithm. So these are the three most used alternatives to solve the surrogate problems that you generate to solve the original one. So how does this work? So this is actually the function that we had at the beginning at the beginning of the talk. Now I'm showing it there, because I want you to see how the whole process is going and how it's find the minimum of the function. So you can think about having initial evaluation just in the center of the domain. There are different ways to do that. If you want to start and you want to initialize your model, you can initialize the model randomly, and you can think about having something more sophisticated like a Latin hypercube in the domain, in which you maximize the information that you get with the first evaluations, and then you build on top of that. But in this case, we just have one of them in the center. And we are using the expected improvement for this example. This is normalized. That's why I don't have any units here. So basically, here this is the expected improvement. What the expected improvement is saying, well, because you have all this band of uncertainty over here, you could essentially collect any point in this region, and that would work for me, right? So what we are going to do is to collect the first one. So we collect the first point, we evaluate the function, and we see how in that point and in a neighborhood the value of the acquisition function drops. And we still have a wide range of points where we can potentially collect. And now we are going to the other extreme of the interval. So we collect a new point. Here we collect a new point. And you see how we start changing our beliefs about the minimum of the function as soon as we start collecting more data points. So you can collect data points. And now we were lucky because here we are collecting a point which is already close to the minimum. So it's kind of the expected improvement is already detecting that something interesting is going on there, because you see how automatically, because this value is way lower than any of the current values that you have, the expected improvement is dropping all the beliefs that it has about other possible locations, and it's kind of removing all this part of the domain of the function, and it's say, well, there is nothing interesting going on here because I think I have something around here. So I can collect a new one. I collect a new one. Look how this is getting narrow. So it's getting more confident about where the minimum of the function is. So basically, I'm done, right? So if I will repeat this over and over, I will keep collecting points here. And you can simply define a stopping condition that says, well, if you start collecting points in the same location in a very small neighborhood, you just kind of stop the algorithm, even if you have more budget to correct more evaluations, right? So this is how this is an illustration of how Bayesian optimization works. This is obviously a toy examples, but now you can think on functions defining larger domains, especially when you want to tune your algorithm and to have something like this happening to find the minimum of the problem. So any questions so far? Yeah. Yeah.
Are there any extra guarantees about finding the global optimum? So if the prior assumptions are met, check the functions with the Gaussian process?
Yeah, that's a very good question. So that's a very good and tricky question. For some acquisition functions, you have some theoretical warranties about how you are getting close to the minimum of the function. Typically, those you can define you can come up with some bounds of how far you are from the minimum, but you typically can't do that for the upper confidence bound acquisition function, because if you think about it, basically if you have exact evaluations of the function that you are trying to minimize, and you have the lower confidence bound in this case, essentially you are creating a bound of the function that you have, such a way that when you collect more and more, the bound is tighter to the function, so you can do some maths and come up with some results with some warranties. But that's typically the case where you have it. Yeah.
Is it really clear that these two bumps on the left in the expected improvement function will not keep increasing so that we actually won't converge and always at some point jump to these bumps?
No, that's nice. So what you are saying now is, well, I want to explore more. I think that the uncertainty I have here should be enough for my acquisition function to keep exploring a bit more in these regions, right? So in the expected improvement, you have a parameter, which is not in the one I presented, but you can add a small parameter to make the expected improvement a bit more explorative, right? So that's what you would need to do here. So this is the default expected improvement.
But it seemed like these bumps were getting larger, like with additional steps when you were doing this, and like.
Yeah, but
Like I was just wondering if these would just keep, like it would seem intuitive to me that
Mhm.
these would keep growing and we actually wouldn't converge because we would.
it can happen. So today you will see in the lab how you will be running these type of things, and you will see how the algorithms start exploring sometimes. But at some point, especially if the function is noisy, it can be the case that, well, if I change my belief about how the uncertainty of my function is, that can change, and you can maybe start exploring another region. And you can even force the final acquisition function to force that to happen. That depends on the acquisition function that you use. The expected improvement, so sometimes it's too explorative. So you're right that it may be stocked in a local minimum instead of jumping. So that's why you need sometimes to modify it a little bit to explore regions in which you could have the minimum there. Yeah.
I guess the performance of this method would depend on the length scale and the prior, right?
Yeah.
So how do you choose the length scale and especially the prior? I would think about the prior. You could see this nice band.
Uh-huh.
But I mean, if you would increase that, you would probably end up try out the other bumps as well.
You're completely right. So to make this thing work, it's crucial to have a good model for the function that you have. It's a clear example that you need to have the uncertainty estimated right. If you have a wrong level of uncertainty, then what is going to happen is that's going to confuse the acquisition function. So you're completely right. Essentially, the way why it works, even if you have that problem, is because at the beginning, so when you start doing the optimization, you typically explore a lot, right? So you start collecting points that kind of give you a general overview of how the function is going to look like. And then as soon as you have a rough idea of how the function is, the acquisition function is going to start exploiting and focusing on a region on the domain, trying to do the exploration.
But that can only be true if your prior is wide enough, right?
Mm-hmm.
If you have a tight prior,
Yeah.
then you find the first bottom
Mm-hmm.
at the first try. This method would probably jump around there because it wouldn't go back because the prior says over there it's much higher.
Yeah, you can imagine all sorts of problems like those, but somehow, yeah. But there is literature having a look to those specific cases and treating those problems. So it's right, but you can solve that. Yeah.
Do you ever throw away data points? Because so now that you have new data points, so we're going to be limited on how many
Mm-hmm.
evaluations we can have just by the computational complexity of the GP.
Mm-hmm.
But as you get more data points, like for example, we have a lot right down at the curve. Can we throw away a lot of them and keep one in order to balance computational complexity?
Mm-hmm. I don't exactly understand your question.
There's like, for example, in that example, there's a lot of data points that are very close together.
Yeah.
But do we need all of those data points in order to keep our approximation of the function which we're trying to model?
Well, maybe you don't need them, but if you have them, you can use the points that you have. So because the problem is that they are expensive to collect, but once you have them, you can use them.
You could throw them away. You could also model it with like a star scale.
Yeah. Yeah, exactly. So if you think about a very complex process maybe in high dimensions in which you have 1 million of data points and you want to do BO with that, well, if you can come up with an approximation, change the Gaussian process that you have, as Alan said, by a sparse Gaussian process, and to deal with that. The problem that you may have is that, well, this can cause some instability problems in when inverting the covariance function, because you will have two rows which are almost equal, right? And then if you want to invert that, that may be a problem. But Mike Osborne has a paper on that, how to deal with that. Tudor?
I was just going to make a comment on one previous question about why the bumps in expected improvement
Uh-huh.
increase. I wanted to say that usually you don't keep the same scale between graphs of the expected improvement.
Ah, yeah, exactly. Yeah, that's a good point. Yeah, to have mentioned that. Yeah, exactly. This is normalized, right? So yeah, that's a good point. Here.
So I was just wondering, is there a connection between this approach and sparse Gaussian processes where you also try to find these anchor points which
Connections. You could use Bayesian optimization to find the point. You can use Bayesian optimization to solve any global optimization problem, including that one, or including the one that Neil was mentioning yesterday. You can directly use a Gaussian process to fit the parameters of another Gaussian process, right? But we'll talk about that later, because more questions here?
Yeah, I was wondering, do we put the condition for convergence on the original function or on the, for example, on the shape of the acquisition function?
Typically, the condition for convergence is that you have a limited budget. So typically, you don't converge because the evaluations of f are very expensive. So you just collect as much as you can. So this is the typical case when the function is very expensive. But if you see that when you start collecting points are very close, so you say, yeah, probably it doesn't make sense to keep getting more. But you put it, well, you can define your own stop criteria, but something sensible is to say, well, if the points I collect are very close all the time, but probably I'm already there and I'm not getting anything else. Yeah.
do you update the hyperparameters after every new data point?
Yeah, so you can do that, but that has a problem, which is, well, you need to update the parameters, so that requires some computational time, right? But that depends on the knowledge that you have on your problem and how much do you think you need to do that. You can think, well, I'm going to take observations without updating that, and then I update the parameters, etc., etc. But yeah, ideally you would like to do so, but you don't need to. Yeah. More questions? Yeah, that's right. So the question is, this looks great, right? So when you say this thing, wow, this is amazing. So we have this problem. Let's use this, right? But if you remember the first reference I mentioned, so the first reference I mentioned, these ideas have been around for many decades, right? So why people are starting to use these ideas now and people didn't do that before. So this question already up. Bayesian optimization depends on its own parameters, right? So that can be a problem because you say, well, I'm solving these optimization problems, but I need a Gaussian process, and I need to feed the parameters of the Gaussian process. I'm replacing this optimization problem by another optimization problem, etc., etc. Okay. Something that you can do is to integrate across the parameters that you have, and that's why they did this paper. Another question that you already made is, well, what happens if my model is wrong? If your model is wrong, probably the optimization is going to be wrong. But luckily for all of us, now we have software to fit Gaussian process. And now you are experts in GPy, and you know how to fit good models and good Gaussian process for the data that you have. And there are these two bits over here, which I think are very interesting. The first one is that, well, good software to apply Bayesian optimization in a black box way, although this is not really a black box. There's been a lack of that, and it's now when different packages and different software are emerging to use these methods, including the one we are developing here in Sheffield and that you will use today in the lab. And I think this is probably the most interesting point and the most challenging area in Bayesian optimization, which is how you can scale the method, right? And you can think about the scaling the method in two different directions. First, in terms of how can I collect more evaluations efficiently, which will be something like, well, how can I parallelize Bayesian optimization to avoid the bottlenecks of evaluating F? And the other dimension in which you can think you can extend Bayesian optimization is how to use it in very high dimensional problems, right? Which is really the complicated bit. So you can imagine I have an optimization problem in dimension 1000. How can I solve that? Because if I use a GP, I kind of heritage all the problems that I have from the modeling of the function in high dimensions, right? So that's the idea. So this is a remarkable paper. So in 2012, the group of Ryan Adams, Jasper Snook, they wrote this paper, in which they said, well, let's use Bayesian optimization to tune parameters of machine learning algorithms, right? Now, some people in the community started to have a look in more detail. What can you do with Bayesian optimization? It was with this paper, and obviously with the work of many others, like Mike Osborne, Philip Henning, Nando de Freitas, and many others. There is a very long list here. I could add that now the whole field emerged. But the nice thing about this paper is that it's a very applied one. I saw how you can use these ideas to tune machine learning algorithms, right? So Bayesian optimization now is becoming a big thing in machine learning. So I just did this yesterday. So if you go and you write in Google Bayesian optimization, you have 40,000 results, right? With quotes, so the whole thing. So you can think that's a large number. And it's a hot topic in machine learning. Also, the workshop in Bayesian optimization in NIPS is becoming like a mini conference itself. So if you're interested in these things and you go to NIPS, I suggest you to go to the workshop. You have other workshops related to this, not only the one which is specifically for Bayesian optimization, but you have things like the AutoML workshop. You have things like constructive machine learning workshops, which are all built around this type of ideas. Right? Yeah.
So, I'm not sure if maybe it's still coming, but I think because you mentioned that Bayesian optimization is very useful for finding the parameters of your machine learning algorithms.
Yeah.
So what immediately comes to mind is two things that you usually have in that situation. The first is that you only have an estimate of your evaluation. So you don't have a precise measurement. You just have, it's you have a confidence interval maybe, or you have some other kind of measuring the uncertainty of your evaluation of the machine learning algorithm. So it would be interesting of how you can handle this. I mean, that's essentially something that I would ask about Gaussian processes in general, because how do you handle the situation where you don't have a particular value, but you know that it is a distribution really that you have at that data point, right?
In the input.
The thing is, the second question would be, when you do this kind of optimization, very often you do have non-continuous parameters to optimize over. So how can you handle that?
Yeah, there is a. I'm going to. So that's good because that comes in the next slide. So there are all sorts of extensions that you can think about Bayesian optimization. So what I just wanted to do here is to give you the intuition about it. But so this slide contains a ton of references of possible extensions that you can think about, including those you're mentioning actually. So you can think. So we will touch those. So we'll get back there. So you can think about doing some multitask Bayesian optimization, right? So yesterday Neil was mentioning about how you can do multi-output Gaussian processes, right? So when you have correlated output, you can come up with some corregionalization matrix that exploits the correlation between the outputs. And imagine that you have a problem which is in which you want to simultaneously optimize different functions, right? So you may have different cases. So if you want to do that, maybe you want to create a combination of the functions and optimize about that. You can think about estimating some Pareto frontiers for the multitask optimization. Or the case that they analyze in this particular case is, imagine that the function that you want to optimize is very, very expensive, but you know that is correlated with another function that you know that is cheaper to evaluate, but is correlated with the first one. So you can use the correlation between the outputs to define an acquisition function that will act on the function that is cheap to evaluate. So you will keep evaluating that, but because of the correlation with the one in which you are interested and that is expensive to evaluate, you can at the same time optimize the other one, right? So this is essentially what they do in this paper, and I think it's a very nice extension of Bayesian optimization. Another thing you can do is obviously what you were saying before. When you have high-dimensional problems, you have a high-dimensional problem and you want to do Bayesian optimization. Typically, you need to make further assumptions on the function that you want to optimize, right? So you can do things like, well, I think that the effective dimension of my function is actually smaller than the dimension of the domain in which it's defined. And you can do things like Rembo, Fernando de Freitas, or you can say, well, I'm going to go for an additive model, right? I'm going to try to have a model that generalizes better across the domain in which is defined, and I'm going to use that in the optimization. So there are different things you can do, and those are just some examples. You have things like non-myopic methods, right? Because all these acquisition functions that you have seen, somehow when they make the decision about where to collect the new point, they are assuming that you have only one remaining evaluation, right? So we are calculating the expected improvement, assuming that I have one remaining evaluation, and I'm going to select the point that will better give me the location with the best improvement with respect to what I have. But think about having 10 evaluations to the future and considering that in the decision that you make. So in that case, probably you don't want to be so greedy about the next location that you want to select, but you want to have in mind and to have in mind that you have still 10 evaluations to define a different strategy for that. So this is somehow like playing chess. When you play chess, the final goal is to win the game, right? But and you don't mind losing a piece on the way if at the end you win the game. So it's the same type of reason. So you are doing some sort of dynamical optimization to the end of the evaluation budget that you have. So these are very, very interesting things. You can think about discrete domains. This is called ARM bandits. So there is a whole literature of optimization in ARM bandits. And you can also see Bayesian optimization like the limit case of that. So if you think about a discrete domain in which you have a probability distribution associated to each point of the domain that give you a utility, right? You can think about, well, if I have all these things are correlated, right? If I have more and more arms, and I take this to the limit, I will end up having a continuous distribution over the domain in which I have. So discrete domains, and you can see BO, as I say, as a limit case of this. You have parallel approaches, and I will be talking about this a bit more. I just include this reference here, but I will show you more later. So the idea is, well, how can I avoid the bottleneck of evaluating F, right? I can do this in different ways. Well, if I can evaluate F in parallel at the same time, that's one thing. Or if I can, if the cost of evaluating my F is defined in terms of the time I need to get my answer, this time may change when I evaluate the function in different points of the domain. I can think about having something distributed, right? So that I can maybe get the answer from my query to the function in one point before I get the answer in the other, so I need to replace that evaluation by other, etc., etc. So that's another extension. You have something interesting, which are how can you do Bayesian optimization with conditional parameter spaces, right? If you think about optimizing the parameters of a neural network, right? You may think about different configurations of the neural network. Some parameters may be involved in one configuration, but not on the other, so they are dependent among each other. So this is a way of defining so what is in this paper, define covariance function for the GP that can take that into account. And obviously there is a wide range of applications of Bayesian optimization, ranging from robotics, and Mark will be talking about that tomorrow as well, to cases in synthetic biology, et cetera, et cetera. So this is the general overview. I don't know if you have more questions, comments? No? Yeah.
So, I mean, as I see it, you have at least 3 optimization problems. You have to optimize the hyperparameters of the Gaussian process. Okay, you have the original problem,
yeah,
problem, and then you have to optimize the acquisition function.
Yeah.
So, what if, for example, you went fully Bayesian and you sample from the distribution of the hyperparameters?
Yeah.
Then you would have, instead of one acquisition function, you would have samples of the acquisition function, right?
Yeah.
So, would that in some way give you a better indication of where to choose your next point? Because it could be the case that you have one realization of the acquisition function, and that optimum that you choose, might not be related to the true optimum of the function. So it might be the case that having samples of this acquisition function, you decide to go somewhere else.
Yeah, you are completely right. In the paper of Ryan Adams and Jasper Snook, that's actually the way they solve the problem of optimizing the hyperparameters of the GP. They go fully Bayesian and they integrate that out. So that's okay. So once that's solved, we still have another problem to solve, which is the optimization of the acquisition function. And Bayesian optimization only makes sense if so we have an optimization problem, and we are transforming that optimization problem into another optimization problem. And that makes sense if the optimization problem that we have at the end is easier to solve than the original one. And in this case, it is, because even if you can have multimodal expected improvement, now you have the gradients of that function. You didn't have that before. Now this function is very is inexpensive to evaluate. So you can evaluate a fine grid and then try to come up with some local optimizers that will give you the global optimum. It's true that you still have a problem there, but typically it's easier than the first one, and that's why it makes sense to use it. But I'm not saying that it's completely straightforward. You can the problem that you have when optimizing the expected improvement, for instance, maybe super multimodal, especially in some cases, as you saw in the example. But the situation is still better than the one you had before, in which you couldn't even evaluate the function as many times as you wanted. But yeah, that's completely right. More questions? No. How are we doing in terms of time? What time is it?
5 past 10.
Okay. Okay. So this is the general overview I wanted to talk about VO. You will have much more tomorrow about this. And what I want to show you now is some things that we are doing in Sheffield about Bayesian optimization. Right? We are doing three type of things. So we are creating a software that you will use today to use this type of techniques. We are going to talk about some scalable methods that in which we have been working in the group, and I will show you some applications. So this application I saw at the beginning about the synthetic gene design for protein production, I will mention a bit about it. So open software. So this is something that we are building here on top of GPy. So this is software we have called it GPy Opt. I guess some of you have already downloaded it in your computer. We will use it in the lab session today. So what is all this about? So basically, GPI-op is a module for Bayesian optimization. It's based on GPI. So that means that any Gaussian process model that is already implemented in GPI, you can use it to perform your Bayesian optimization, which is great because you can now use a sparse GP. If you want to solve a problem in which you want to collect a lot of data points, you can use a multi-output GP, etc., etc. So you all know that. So you have all these things, and we have also implemented some parallel optimization methods, right? So methods in which you can evaluate the function in parallel using the core that you have in your computer. So I've been developing this together with Wen. Mainly, so hope you like it this afternoon. But we will be very happy if you want to contribute or if you have any criticism of how we can improve it. So what we have tried when implemented GPI-op using GPI is trying to target the different users that may be interested on using Bayesian optimization. So we have three, let's say, ways of use of Bayesian optimization using GPI-op. So you have a first way of using it, which will be mainly the one we were using in the lab today, which is some modular Bayesian optimization in which, well, Bayesian optimization is mainly these two bits. One is the model that will be a model that you will import from GPI and an acquisition function, and you have a number of them implemented, so you can change a lot of things in the model that you have, as you will be able to change a lot of things in the different acquisition functions that you will be able to use. And there is a number of optimizers for this acquisition function. So things like direct, CMS, they are all wrapped into GPI-op, so you can try different ways of optimizing that. So we have implemented this class here, which is an auto tuner. So this works like any optimization method that you can get from GPI. So that's minimization, and essentially the objective of this function is you don't really care about what Bayesian optimization is, but still you want to use it. So you have a function, you plug the objective function here, the bounds. We still need to extend this for more complex domain, but you put it there. It's not optimized to be fast, but it's optimized to be good. So in the sense that it will provide you probably a good solution to the problem. So somehow we have selected the default parameters from here. And something we have done, this is already working, but still we have some things to improve, is if you are a user of Spearmint and maybe you want to try GPI-op, something you can do is to use a very similar interface. So essentially, if you have your problem defined in a JSON file, in which you determine the type of variables that you have, the type of likelihood that you want to use, etc., and you have the problem defined, which will be a computer model in another file. You basically have to write in the console of Linux GPI-op the folder that you have, and the program will automatically solve it for you and will generate a report with the results, basically. So that's the idea. So but you will be using this this afternoon. So I'm going to mention now about something we have been doing here about how to scale Bayesian optimization, which is, well, so imagine that the price of evaluating the function in one location is the same of evaluating the function in many locations. Computationally, this may be because you have many cores to do that, or in experimental setting because running parallel experiments in the lab is as cheap as running just one. So I'll go just briefly over this. So essentially now, whenever you don't need to decide just only one location, you need to design multiple of them, right? And to determine an strategy how to do that is what we're doing here. Just a bit of notation. Y and this is representing just to keep updated the iterative idea that we do when collecting batches. So yn represent the available data when we have the available information when we have n data points, which means the GP structure, the parameters of the GP and the data set itself. And alpha x represent any acquisition function right? So the idea was to develop a method that could be used with your favorite acquisition function. So this is a bit tricky with the notation. So this is how you would solve the sequential policy in terms of how would you use a sequential policy, which is essentially what we have been talking about in this talk, using this notation. So basically, now you have, in a sequential policy, you can consider that you have batches of size 1, all right? So this is the information that you have when you want to collect the T batch, and there is 0 batches in that 0 elements in that batch, right? So this is just a way of saying, well, if you want to follow a sequential policy, you just maximize the acquisition function. So now when you design a batch, you can think about 2 different ways of doing it. So you can go for a non-greedy approach. So you could say, well, if I have expected improvement, I can jointly optimize the expected improvement for a group of points. Or you could do this in a greedy way. You would say, well, I first select the first element in the batch, and then the second one, and the third one, and you do that iteratively, right? So we are following the second approach here. And you have this ugly formula. You don't need to look about it. The idea of this formula is, well, if I collect the first element, and I now want to collect a second element in my batch, essentially what I have for the first element is not an evaluation of my function, but I have the predictive distribution of the GP, right? So when it comes to select the second element, what I have is not a single acquisition function, but I have a family of acquisition functions corresponding to all possible values that my first location could give me, right? So somehow you need to integrate that out before selecting the second element, and so on and so forth. So you enter in this loop, which is a loop in which you need to maximize the acquisition function and then integrate out what you have, maximize, marginalize, maximize, marginalize, right? So the problem, and this is what this formula is representing, where this bit here is the predictive distribution of the GP, and this bit is basically representing the optimization step that you need to do every time you marginalize the previous observations in the batch. So you can do this, but this is computationally very expensive, as you can think. This doesn't allow you to collect batches of a very long size, and the literature has been very well aware of this bit and has tried to come up with different approximations to not having to integrate out these iterative steps that you need to do. So essentially, so the bottleneck in all this process is, well, every time I collect a new element in the batch, I need to update the Gaussian process. That can be expensive. You can think, well, I can use a sparse GP or a distributed GP, but still this applies for all the technique that you have. So if you have a way of avoiding updating the GP every time you collect a new element in the batch, that's better in any case, right? So the method that we develop here is, well, so we want to use the predictive distribution of the GP, but we don't want to use it explicitly, right? So is there something in the function that will allow me to do that? So and we come back to the original hypothesis that we have here, which is that the function is Lipschitz continuous, and if you have a look to this constant, and you reinterpret this constant, and now I'm talking about maximizing instead of minimizing. So what the Lipschitz constant is giving you is a way of bounding the function that you have, right? So essentially, if you say, well, I think I have this function here, I have collected these evaluations. These evaluations in my current best, so I think the maximum is here, right? And I have some fixed value of this Lipschitz constant that I know. So whenever I evaluate the function in a point, because of the Lipschitz constant is bounding the change that I allow in my function, this is creating these cones that is defining exclusion zones where I know the maximum, in this case of the function, doesn't belong to, right? So this is the idea. I say, well, so let's use these functions to define exclusion zones where we know that we don't have to collect points, right? And let's use this this idea to create the batch that we want for our optimization. So now, this is for a fixed function, but now what we know is that this f is not a deterministic f anymore, because what we have is a GP based on all previous observations that we have. So now we know that the marginal distribution at any location of the domain is going to be Gaussian. So we can come up with a probabilistic version of the balls that are described by the Lipschitz constant of the Lipschitz constant continuity of the function. So now what we have is, yeah.
Sorry, maybe I missed it. How do you estimate this constant? Because if the constant can only make if you have an estimate.
We'll get there. We are not there yet.
Sorry.
Yeah, it's a critical parameter. Yeah, we have. I saw a way of how to do that. So the idea is, well, let's define some functions which represent these cones, these exclusion zones that the Lipschitz constant is giving me. And these functions are essentially going to be defined as the probability of not given a point in the domain, the probability of the maximum not being in a neighborhood of it. So you can think about these functions like, well, this function is going to be very small around the point I have collected, and it's going to grow up to 1 for regions which are far from the point I'm looking at. So these are somehow these will be penalizers of the acquisition function, I anticipate. So essentially, these functions are going to represent our beliefs about where the maximum of the function is, using this property of the function that we had at the beginning, but without using explicitly the GP that we have. So this is what we had before. It's very expensive to evaluate. We want to replace this by something that is cheap. So instead of doing this marginalization loop, we are going to replace this by something that maximizes and penalizes directly the acquisition function by using these probabilistic exclusion zones that we define using the Lipschitz constant. So this is an idea we're doing. So we start with an acquisition function which looks like this. So you just want to collect one element. So you maximize the acquisition function. You get this point here, right? And now what you do is you build this exclusion zone based on some value of the Lipschitz constant, and I will say how to estimate that. So this is the penalizer that is determined by that exclusion zone. And when you multiply the original function times the penalizer, what the effect that this has is essentially you drop the value of the acquisition function at that point. So you have another acquisition function that you can now maximize again to create a new penalizer. You drop the value there, and you go on and on collecting batches. So all you are trying to do is, by means of this penalization that you do, you are trying to emulate what the change in the acquisition function if you were able to collect a point in the domain, right? So now what you do is, well, now I don't have to do this loop of marginalizing, optimizing the elements of my batch. I'm replacing that by something which is a positive transformation of my acquisition function. I need my acquisition to be positive, and that's what this G does, times the penalizers that I create every time I collect a new data point. So basically, you have completely removed the marginalization step. Now you don't need to do the integral anymore, and you simply replace that by the maximization of this function that you need to do when you want to collect each point in the batch. So I did this a bit fast, but I get you at least get an idea of what you're doing. So this is something we did here with Neil, with Senwen, and with Philip Henne that will be tomorrow. So this is the intuition, and now I come back to your question. So this is an acquisition function for a problem. We don't care what that is. So you see, these are different regions with different values of the acquisition function. You think, well, essentially, I want to explore the modes of this function over here and come up with the batch. So this is essentially representing the effect of these penalizers on the acquisition function that I have. So I have done this in this example, for a value of the Lipschitz constant, which is 50. But if I change that value, what you see is that that has an effect in the size of the penalizers that I'm using, right? And if you think about it, this is very interesting because now, if you remember the exploration-exploitation trade-off that we were talking about when we wanted to select a new element in the data set, now we have this exploration-exploitation trade-off, but for the whole batch that we are collecting. And actually, this constant is representing this exploration-exploitation trade-off. Because what happens is we have a very large L, we are allowing very drastic changes in our F, and if we collect something that is very good because maximize the expected improvement, then because we will keep collecting points around it. If you decrease the value of that, you will be exploring more the space, and we will be exploring different modes of that. So now the exploration-exploitation trade-off is in two places. Is in the acquisition function that you are using, in the way you define your acquisition function and you use it to collect the points, and in the way you collect the different elements in the batch. So that's the idea. So how do you estimate L? So if you know something about how is the change, how the maximum allowed change to the function, you can select that. But now you have a GP, and the gradient of the GP is multivariate Gaussian, right? And something we know is that we have a function f, which is Lipschitz continuous, and we take the maximum value of the gradient of the function. You can change the norm here, and this holds for different norms. This is a valid Lipschitz constant. So what we are going to do is we are going to take what we know about the gradient of the function, which is in our GP, and we are going to maximize the gradient, and we take that value as the Lipschitz constant that we use in our law. So essentially, we use what we know. So we have the GP. What we know about the maximum allowed change by the GP is what we know about its gradient, and we simply take the maximum of the gradient of the GP.
Doesn't this tend to be an underestimation of the Lipschitz constant?
Yeah, you are completely right, and the effect of that is that's completely right, and the effect of that is that you start exploring a lot, which is not a problem, because the more you explore, so that automatically, you will see in some experiments how the method is working very well, that automatically is forcing the method to explore a lot, to collect points in the domain, and as soon as the method starts to know what is the shape of the function, that will start to converge to interesting regions. But it's true, you are underestimating the value of the Lipschitz constant. Yeah. You could potentially say, well, I have this uncertainty here, I haven't used it, or I can come up with a different estimator of that. There are many, you can think about many different ways of doing this. This is one that is fast, and we tried it because this is all an heuristic, right? So we were happy with the result. Yeah.
Do you have one single Lipschitz constant, or do you have one for each data point?
In principle, we have one Lipschitz constant for all the domain of the function, but you could think about extending this straightforwardly to cases in which you have an heteroselective function in which different Lipschitz constant may apply to different regions of the domain. You could potentially even use the gradient of the GP in each point of the domain and doing that. Yeah. So we did that. So we did some experiments. So basically, we compare this with, I guess, I hope almost all methods to do parallel Bayesian optimization in the literature. And what we did was to compare this in terms of the computational time that you need to get the optimum of the function. So just a disclaimer here. So we are in the comparisons, we are using other people's code. And we have code implemented in R, code implemented in MATLAB, and our own code that is implemented in Python. So the difference that you see here are difference in terms of the method that are used and also in the implementations. So basically, this is what we got. So we have the subtle function for different batch sizes, which is what I'm representing here, for different dimensions. What we did is we ran the experiments giving 1 minute budget per dimension of the problem. And we stopped when the time was over, and we collected the best result of each one of the algorithms, right? Essentially what we see is that, well, these methods, we tried this for two acquisition functions, like the expected improvement, the upper confidence bound. We run the experiments, and yeah, we see that this is working very well. It's scaling very well with the dimension and with the size of the batch as well. And you see these two methods are non-greedy methods that optimize at the same time all the elements in the batch. And the problem of that is that they are more fundamental, but they scale worse with the dimension of the problem and with the number of batches that you have. So we did this for many other experiments, for a function in a very large domain. So these are the methods that we have, and this is the current best in time seconds. So you see the difference here are determined by how fast the methods are able to make the evaluations because of the approximation they're doing. Another example, this is 70-dimensional example. The two methods that use the penalization work very well. This is an example tuning the parameters of super vector regression. So you will do something similar today in a yeah.
How would this function look like if you plot it with respect to number of function evaluations?
Yeah, we have that in the paper. Yeah, but I don't have in the presentation. I can show. Yeah, it's slightly different, but still in terms of the information collected by these methods, they are still better. Sometimes they are very close to other methods that collect the same information, but because you need more time to build the batch in terms of the computational time, this tends to be better. So this is another example. So essentially it works very well. So I'm almost done, right? Yeah. So just to mention, so this is just a final application. I mentioned at the beginning how you can use these ideas to design synthetic genes to empower cells to produce protein of interest. So the general idea, so you have a very complex process that determines the cells. You have different rates at which things are produced, and you want to optimize those rates depending on the gene that you have. So this is we'll skip this bit. So essentially, what we are doing here we came up with a way of defining genes using Bayesian optimization, which are based on some features of the original gene sequences. We have a multi-output Gaussian process that controls the different aspects of the biological process that is going on. The average expected improvement, etc., etc. I will skip this part. And this is just an illustration of for some genes that we are low expressed, how good you can do and how much you can improve by optimizing the genes using BO. So that's all I wanted to say. So just wrapping up. So I think Bayesian optimization is a fantastic tool to solve optimization problem. The model and the acquisition function are the two most important bits. And you can define your own acquisition model, do your own acquisition function depending on the problem which you may be interested. Many useful extensions. I think the current challenge of BO is to scale up the method to a large number of dimensions and for a large number of data points. So there is a lot of several packages out there. So I suggest you to use them, and I suggest you to use GPyOpt that you will be playing with it today. So many thanks to many people. So to Neil, to Semwen, to Philip, and also to Mike Osborne. We are doing very interesting stuff, and I learned a lot from them by doing this work. And to some people in the CBE, we are collaborating with them doing this design of the genes. Just one last bit. This is something that Neil always mentioned, which is, well, when he goes running to the Peak District and thinks about which way to go, you can explore or exploit different new routes. So there are two selling points here. First, if you are going to stay here during the weekend, please go to the Peak District and use, if you haven't been there, use a pure explorative approach to discover the many nice places that you can find there. So that's it.
One question concerning this Lipschitz constant. like choose or look for Lipschitz or maybe Hölder constant for the second derivative, better exclusion areas. Do you know if there's any work been done in this direction?
I'm not aware of it, but that sounds like an interesting extension. Yeah.
This is a short question regarding the speed of the optimization. You only compare with other Bayesian optimization algorithms. Is there? I'm not into optimization myself. Is there other optimization algorithms that you could have compared with regarding speed? So it's Bayesian optimization the fastest.
I understand. Yeah, of course. Yeah, you could do things like direct or some evolutionary algorithm to do that, but I haven't done that because. So when you do Bayesian optimization, you are comparing with Bayesian optimization methods because in some papers it's already proven that these things improve all these other alternatives. There may be cases in which not, but in general they do. So that's why I didn't include those here. Yeah.
So you mentioned the discrete and continuous space and the conditional space. How do you optimize the acquisition function there? Because you can't apply CMES or direct because they transfer.
We are not there yet. We have implemented that in GPy, op, and the cases that we have are continuous spaces defined with box constraints. We are thinking about it, but we haven't touched that problem yet. More question? Well, I think coffee is ready then.